Hello everywhere, my name is Cleiton Marques. I am a graduating student in computer engineer from Universidade Federal do Rio Grande. Durante this presentation, I will talk about the project I have been working on, entitled Software Reliability of SRAM cells during the three operation states. This work has been developed by me with the orientation of the professors Cristina Meinhardt and Paulo Butzen. Durante this presentation, the following topics will be covered: introduction, radiation faults, SRAM, methodology, results, and conclusion. Starting with the introduction, computer systems had a main function, the storage and processing of data. This data is stored in digital systems, those the memory circuits. When we talk about memory, it is necessary to reconcile three main characteristics: the storage capacity, speed, and manufacturing cost. However, even today, it is impossible to meet these characteristics in a single memory. Therefore, for each specific function, we use a different memory technology. So you extract the best characteristics for each type of memory. This work evaluates SRAM memories, which are a circuit widely used in cache memories. These memories have a high performance, but a very high manufacturing cost per bit. The main motivation for this work is linked to the critical impact of nanometer technologies on the sensitivity and reliability of SRAMs. The semiconductor industry's demand to reduce the size of integrated devices has enabled a major advance in the performance of computer systems. With the technology advance, transistors are such ever small dimensions. In the year 2000, a chip contained about a million transistors. Currently, this value has such a billion transistors. This means that in some area today there are a much large number of transistors. This reduction in the scale has impact on memory circuits that are more sensitive to interference from external environments. That is with greater difficulty in keeping the data storage. For example, when a particle Z collides with the transistor, it deposits part of electron latons in the region of the strike. If this region if its collision occurs at the p-n junction of a reverse polarized transistor, the transistor collects this charge. If the observed charge exceeds the critical charge supported by the device, it will present a behavior deviation or a bit flip. The main fault responsible for this behavioral deviation in memories is called a single event upset. The figure that contains the yellow marks indicates the occurrence of bit flip in memories. The other figure illustrates the location of the fault of Atlantic South, an anomaly in the magnetic field of Earth. Your region is one of the most affected by this type of fault. This shows the importance of studying this type of event mainly in your region. Talking about SRAM, SRAM structure, this is an illustration of the basic structure of a SRAM. The thread to main memory address we have the line and column decoders for select the correct cell. In this work, a column structure has adopted. Where also 4 cell topologies were evaluated. The 60 cell, most used in industry, 80 with dedicated read mechanisms, 90 cell which does improvement of the 80, and the 80 soft error robust cell propose. To build the complete architecture of SRAM, the right sense amplifier and pre-charge circuits are used. Since the HT software robust cell works with a pre-charge on ground, some circuits have been adjusted. For example, pre-charge and sense amplifier. This work has developed a total electrical simulation. The first step has the shows of the simulator. The Energy Spy simulator has used. The next two steps consist of actions related to description on validation of the circuits and implementation. After that, the analysis of time and consumption, noise tolerance, and radiation robustness are performed. For automation of the simulation process and interpretation of the simulator outputs, Python scripts have been prepared. Finally, the results of delay, power, and static noise margins and latch threshold are found. To explain how a single event set simulation is performed, we initially have a think about the physical event of the particle strike. This event trigger a series of mechanisms. We can measure these interactions to an analytic model. The model concepts are described in the simulation implementations, and finally, by running of the simulation, this event is simulated. After the development of all steps, we arrive at the following results. Talking about time evaluation, HT cell obtained the lowest write delay, but the 60 obtained the lowest read delay. Evaluation energy consumption. In the energy consumption, the cell HT obtained the lowest consumption, followed closely by 90 cell. Observing the noise tolerance results, the 60 cell demonstrate a warning sensitivity related to read operation, while 80 cell software robustness proposed achieved the best noise results. The noise tolerance is divided in three characteristics: hold static noise margins in hold state of cell, read static noise margins in related to read operation, and write static noise margin in write operation. For radiation results, considering the worst case, the HT software robustness proposed cell obtained the best robustness result. Evaluate the auxiliary circuits. During the operations, the read had a most critical point, relating the greatest impact of 0 to 1 simulations. 0 to 1 simulations, cell stored the logic value 1 that's forced to 0 by the particle collision. Simulations 1 to 0, cell storage the logic value is 0, that's forced to 1 by the particle collision. Through this work, we can conclude that the 16 cell obtained the best read results and is the cell with the lowest number of transistors, but it obtained the worst noise tolerance result during the read operation. The HT cell obtained the best result in write delay and the lowest energy consumption, but its array has a higher number of transistors than 60. 90 cell did not obtain the best result in any of the points analyzed in this work, but had results very closely to HT. However, it has the higher number of transistors between the cells. The 80 software robust proposals presented a concept of isolation between the internal nodes. Uh, this is a complete protection of the storage data in half of the simulations it's as submitted to. It also presents the highest noise tolerance in all three operations, and yet when it has affected, has a greater robustness to the affect a single event upset. However, it has a show much longer delays than the other cells and extremely high energy consumption. Speaking now about the auxiliary circuits, the right circuit has the most robust considering the roast case. The pre-charge circuit has the lowest number of sensitive nodes, but a fault in the circuit affects both operations. The sense amplifier circuit had the highest sensitive and the highest number of sensitive nodes. However, some faults cause only read errors. In auxiliary circuits, the critical point is the bitline nodes, as they connect all the cells in the column with the auxiliary circuits. So, total development of this work, it has possible to verify and evaluate the fundamental metrics related to delay, noise, and consumption, the critical charge and the latch threshold of both cells. It has verified the increase of the sensitivity of SRAMs as the decrease of the technological node, and the effects of propagation of radiation faults in auxiliary circuits to the internal nodes of the cells. So thank you all for attention. Any question you can contact via email. And again, thank you so much.